A very good afternoon to each one of you. On behalf of Bangalore Chamber of Industry and Commerce, we welcome you all for this special session on design of heavy-duty hydrogen engines. The session is addressed by Dr. Lakshmi Narayanan, formerly CTO of Simpson & Co. Thank you very much, sir, for accepting our invitation to address at this important session. The program is moderated by Mr. Rabindra Saw, Chief Engineer at Tata Technologies, and who also chairs the Publications and Corporate Branding Expert Committee of the Chamber. Thank you very much, sir, for structuring and initiating this session. The Chamber acknowledges the support of our annual sponsors of member organizations, Messrs. Bueller, Fundermax, IAMPL, MTR, Sona Group, SDMIMD, TVS Motor, Vishwas Group, and Wipro for their support in the activities of the Chamber. Thank you very much once again for all the participants for joining this session. And now I hand over the stage to Mr. Rabindra Saw. Over to you, sir. Thank you.
Thank you, Dr. Lakshmi Narayan, sir, for being taking time and sharing your knowledge on a very important topic of design in heavy duty hydrogen engines. It's a very complex and difficult subject. I'm moderating the session, and I'm working as Chief Engineer Strategy Project at Tata Technology based at Bangalore. I would like to introduce our guest speaker, Dr. P.A. Lakshmi Narayanan, is formerly Chief Technology Officer, Samsung and Company, and currently he is based at Chennai. Dr. Lakshmi Narayanan studied in Indian Institute of Technology, Madras, for his Bachelor of Technology, MS and PhD degree. He worked at Loughborough University of Technology and Kirloskar Oil Engines Limited for about 5 and 20 years respectively in both the institute, before moving to Ashok Leyland in 2002 to head the engine R&D division. From 2011 till 2019, he was the Chief Technology Officer and Technical Advisor at Simpson Company Limited. Now he teaches at IIT Kanpur and industrial academias. With his team, he has developed more than 8 diesel and CNG engine platform and around 150 engine types commercially successful for efficiency and cost effectiveness. 2 engine designs received prizes from the Institute of Directors, India. 12 ideas were patented during the development of engines for over 40 years. 40 years. Sir has also authored 54 research papers in journals and conferences of international repute. Four of them received prizes for integrity and quality of contents from SAE, R. Colwell Award, Combustion Society India, AVL GRAS and AVL India in 1983, 1993 and 2005 and 2011. He is also the recipient of Automotive Engineer of the Year Award from the Institute of Automotive Engineers India. Now it is known as SAE India in 1994. And Lifetime Achievement Award from the ISEES 2021. He has co-authored 2 books titled Modeling Design Combustion, Springer first edition in 2010, second edition in 2021, and Critical Component Wear of Parts in Heavy Duty Engine, John Wheeler 2011. He is co-edited a handbook, Design and Development of Heavy Duty Diesel Engines, and it is covered in Springer 2020, and his 4th book, Thermal Management Engines in Springer 2021. He is elected to the Fellowship of SAE 29, INAE 2030, and ISEES 2018. With this introduction, so much of Indra's experience. Thank you so much, sir, for your time and sharing your knowledge. And now I hand over to you, and stage is yours, sir.
Thank you. Thank you for the introduction. Let me share my slides.
Yes, sir.
So I hope you are able to see my slides.
Yes, sir. We are able to see.
Yeah. So good evening to everybody. The topic I have chosen, or we have chosen, is a design of heavy-duty hydrogen engines. Hydrogen is a fascinating subject. In fact, most of our universe is covered with hydrogen. Hydrogen is the main fuel which is used up in nuclear reactions in the entire universe, and that gives us light and energy. But unfortunately, all the hydrogen on the earth is trapped in the form of water mainly. So we have to devise methods to separate hydrogen from water, and it needs a lot of energy. It is hoped that this energy can come from renewable sources, mainly the windmill and the solar energy. Both can generate electricity, and that electricity can be used to split water to hydrogen and oxygen. This is a long way off, maybe around 10 to 15 years. Also, we have another difficulty. Though per kg mass of hydrogen, we have a lot of energy that can be released by burning it. Hydrogen is very light, and hence to store it has become a big challenge. So storage of hydrogen, especially for moving vehicles or automobiles, is a challenge, and it is a great engineering job that is being carried out by many companies. Today, we will talk about the hydrogen engine and very less about production of hydrogen, storing and transporting it. So the contents of today's topic is split into two. One is basics, where we will talk about the flame velocity, flame temperature, production of nitric oxide while we burn hydrogen in air, quenching distance, which is very important for the layout of the engine, ignition temperature, ignition energy, compression ratio, diffusivity, and density. And based on these basics that we talk about today, we will describe what are the design challenges when we build a hydrogen engine, and some of them are ignition system, crankcase ventilation, and how we are going to adapt hydrogen combustion to make it very efficient and with less emissions within the engine, avoiding after treatment. So it drives us to the topic of lean burn engine, and lean burn engine with pre-chamber combustion seems to be the ideal. So we will give some practical examples which have been successful in applications like trucks, buses, and off-highway vehicles, where the duty is really heavy. So also at the end, we have listed references. Those who are interested can go through them. First, we will talk about combustion. Hydrocarbon combustion is very well known. When we burn hydrocarbon with oxygen, we get carbon dioxide and water. This is very simply said, but the combustion is never complete. So we get traces of carbon monoxide and hydrocarbon, which fall under the category of regulated emissions. Interestingly, the high temperature of combustion creates a nuisance, namely a nitric oxide. atoms. The nitrogen in the air is not remaining quiet, even though it's a neutral gas. A very little part of that reacts with oxygen at high temperature and produces nitrogen oxides, namely nitric oxide and nitrogen dioxide. And we produce more nitric oxide if the flame temperature is higher. So one of the techniques that we follow in the hydrocarbon combustion is to moderate the flame temperature to produce less nitric oxide inside the piston engine. Coming to hydrogen, we have hydrogen burning in oxygen, producing an end product of water or water vapor, which is very good and highly neutral. But hydrogen also burns at a very high temperature, as we are going to see in the next few slides, and contributes to production of nitric oxide. Whereas we are able to burn hydrocarbon very well, hydrocarbon like gasoline or petrol, very well inside an engine at an air fuel ratio of 1.0, that is at ideal, chemically ideal proportion. We find burning hydrogen at chemically correct ratio produces exorbitant amount of nitric oxide, basically because hydrogen burns at a very high flame temperature. So we will see the details a bit more later. So we got rid of carbon while we use hydrogen, but we still have nitric oxide. So now we see the chemistry first, then we will see the physics of hydrogen combustion. We will see about something about flame velocity, flame temperature, and nitric oxide. And we will also see what the flammability limits are of hydrogen compared to other fuels that we use today in spark ignition engines. We will talk a bit about the ignition energy and ignition temperature. We have two types of flames, namely laminar and turbulent. You can see here the laminar flame is very quiet and very slow, and when it is turbulent, we find the flame front is wrinkled. On the right side, you will see a thin flame front, that is the edge of this flame, shown as a simple line, and it is of thickness very small, delta L. And from the left side, the gases are flowing at velocity SL, and they get burned at the flame front, and on the right, they go with a velocity which is slightly enhanced by a factor 1 plus tau, and tau is obtained by the decrease in the density by virtue of the increase in temperature while after the fuel is burned. So this is called, this velocity of the unburnt fuel air mixture is also known as the laminar flame velocity, and it is called SL. And after it is burnt, it goes at a higher velocity, which is 1 plus tau times SL. When we look at the turbulent flame, we find that the flame area is enhanced, as shown by the red line. You can see the red line. It is enhanced because the flame is highly wrinkled. So the flame area is essentially higher, but also the flame thickness apparently is more, and it is delta T. Delta T is higher than delta T is higher than delta L, but it is looking like a brush. The turbulent flame velocity is therefore equal to the flame area ratio of turbulent and laminar flames times the laminar flame speed. So if you look at the minute portion or a small infinitesimal portion of this wrinkled flame, it looks like a laminar flame. But the essential area or the equivalent area of the laminar flame is many times higher than a normal laminar flame, and therefore we observe a very high turbulent velocity. That means the unburnt fuel has to move at a higher speed for the flame to remain at the same point in space. So this is called the turbulent flame velocity. And of course, the burnt gases move towards the right at a higher velocity, which is enhanced by the increase in temperature. Then we will define the equivalence ratio and air excess ratio. The engine engineers or designers would like to use the term air excess ratio, and the combustion engineers favor the use of equivalence ratio. So all the science of combustion deals with phi, and engine engineers handle lambda. The equivalence ratio is defined as the ratio of stoichiometric air-fuel ratio to the actual air-fuel ratio. Stoichiometric air-fuel ratio is the chemically correct air-fuel ratio. And lambda is the actual air-fuel ratio divided by stoichiometric air-fuel ratio. In other words, phi is reciprocal of lambda. So there is not much difference, but we must know this while studying the literature. When phi equal to 1, combustion is stoichiometric. When lambda equal to 1, combustion is stoichiometric. However, if phi is less than 1, the combustion is lean with excess air, and for this, lambda should be greater than 1 for the combustion to be lean. And when phi is greater than 1, combustion is rich, and this corresponds to lambda less than 1. So we have defined the terminology. Now we take some of the graphs from the combustion engineers. On the left, you see the laminar flame speed of gasoline. On the right, we see the variation of nitric oxide with respect to equivalence ratio. So towards the left, it is lean. Towards the right, it is rich. You can see. Here we have plotted the laminar burning velocity at various pressures. At low pressure, the laminar burning velocity is higher. At higher pressures, the laminar burning velocity is lower. That means the flame propagates at a lower speed at higher pressure. So in the engine, where we have around 8 to 10 bar or 14 bar at the maximum at the time of combustion, we have slower laminar flame than what is shown in this graph. So it will be somewhere here. So there are methods to estimate the flame speeds at higher pressure. But what is interesting here is the flame speed seems to be maximizing somewhere around phi equal to 1, or when the air-fuel ratio is stoichiometric. Similarly, nitric oxide is maximizing somewhere around stoichiometric mixture, but the graph shows it is maximizing at equivalence ratio 0.9 or lambda 1.1. If you look at the, if you look at the sorry, one second. If you look at the flame temperature, we find flame temperature also is maximizing at about lambda equal to 1 or phi equal to 1. This is for gasoline. If you go for natural gas, which has got 4 hydrogen atoms and 1 carbon atom per molecule, the behavior is similar, but only thing is the flame speed is higher for natural gas. We have already guessed with a higher hydrogen content, the flame speed seems to be increasing. Okay. And the nitric oxide is again high, somewhere around phi equal to 0.9, just like what we have seen in case of gasoline. If you look at the flame temperature, again it is maximizing somewhere around phi equal to 1, but the flame temperatures are slightly higher than what we have observed in case of gasoline. Finally, we come to hydrogen. It's very interesting. The graphs are similar in trend. The NOx increases and then NOx increases, then decreases, and around phi equal to 0.9, NOx is maximizing as we have seen in other cases. And the flame speed also seems to maximize somewhere around equivalence ratio 1. But here you will see it is maximizing around 1.5, very near to 1. But the speed, the laminar flame speed is 7 times faster than gasoline or natural gas. So hydrogen burns very, very fast. If we look at the temperature, you can see that dashed line which represents the hydrogen flame. It is again maximizing somewhere around lambda equal to 1 or phi equal to 1. But the temperatures are 300 to 400 degree higher than gasoline or methane. And that is the reason we end up with very high nitric oxide compared to gasoline at phi equal to 0.9 or lambda equal to 1.1. So we have to beat this. We'll see the techniques. The flammability limits of hydrogen is really very, very wide. We'll see the details in the next slide. If you take any fuel, if you have too much of fuel, here for example, the flame does not sustain itself. Or if you have too much of air or oxygen, then the flame cannot sustain itself and it will cool. It will be cooled by the excess air. So there is a very small range of fuel concentration where this flame can sustain itself and will not be quenched or stopped. So this is known as the flammability limit, and you have both upper and lower flammability limit for any fuel air mixture. We'll see some of the fuel air mixtures that we come across in our daily life. First we see diesel, and here we have plotted the fraction of fuel in the air as volume percentage. The top one is diesel. On the left side you have lean and right side you have rich fuel. And this arrow shows where the stoichiometric mixture lies. So essentially, we have a very narrow range for diesel flame to sustain. Next, we have methane, which is nothing but natural gas in essence. That also has a flammability limit range, which is slightly wider than diesel, but not very wide. So that is, the width is around 12%, whereas for diesel it is about 5%. If you go for gasoline, you have a width of around 6.6%, which is slightly better than diesel and less than methane. That is because the number of hydrogen atoms in gasoline, for example, is more per carbon than diesel. If you come to hydrogen, you see the stoichiometric composition is somewhere here, and that is also shown on the right side by this arrow. And we have a very wide flammability limits. That means the range is from 4 to 75%, which is really very wide. Some of the calculations are given on the right side on the top, how to estimate the stoichiometric composition. Now we come to hydrogen. It is easier to start a lean mixture. In fact, in gasoline engines, we struggle to run a mixture lean, mainly to reduce the production of nitric oxides inside the engine. And it is a great struggle. So most of the time we have given up in the earlier days. With the GDI, yes, we are able to manage somewhat lean mixture because GDI imitates diesel fuel injection. Okay, but hydrogen is able to sustain very lean mixture in combustion. So running lean will reduce the fuel consumption. That is because whenever we combust a fuel, we are increasing the number of atoms per molecule. When you increase the number of atoms per molecule, like H2O or CO2, for example, the specific heat, due to the change in specific heat with respect to number of atoms per molecule, we have the ratio of specific heats affected, and this is actually an affliction that internally reduces the energy that can be shown as thermal energy during combustion. Some of it is absorbed as the is absorbed by to move heavy molecules. Okay, so we don't want to increase the number of atoms per molecule in combustion. So if you are able to run it lean, we are able to run the engine more efficiently. We will see some of the graphs after some slides. So lean combustion therefore reduces nitric oxide because we are reducing the temperature, and this has got a negative or disadvantage. If you try to run lean for the same year, you can burn less fuel, therefore you can produce less power. So power to engine swept volume can drop. Okay, we will see how we can solve this problem. Next is ignition temperature. Ignition temperature of hydrogen is very high. Of course, natural gas also ignites at a high temperature, but it is somewhat less than hydrogen, whereas gasoline can be ignited at a lower temperature. More beautiful is diesel, which can ignite at a still lower temperature, but we are not considering that here, considering diesel here for comparison, because we are going to burn hydrogen as a spark ignition engine fuel. We cannot run it as a compression ignition engine fuel. Why we cannot run it as a compression ignition engine fuel? The question is answered here itself. The ignition temperature is so high, regular compression method cannot reach this temperature inside an engine. So this table gives the comparison of hydrogen and gasoline for ignition temperature. Because the ignition temperature is high, the octane number of hydrogen is far higher than 100. And we are struggling to maintain gasoline at around 95, 96 in our practical cases. And hydrogen can reach 120 as octane number. So what does it do? It enables us to increase the compression ratio and avoid auto ignition, and which is limiting compression ratio in gasoline engines. Now we can go for higher compression ratio, and thermodynamically we can reach higher efficiency because of higher compression ratio. Also, we can go for really advanced timing and improve the efficiency of the engine. And the hydrogen ignites at a high temperatures, therefore it can easily resist knock. So we can advance timing and increased compression ratio without any nuisance of knock, which is a big problem both in gasoline and CNG engines. Now comes the ignition energy. Interestingly, though we need high ignition temperature, we need very less ignition energy to create or strike a fire in a hydrogen air mixture. So hydrogen is easy to ignite a lean mixture. If we compare gasoline vapor, which needs 0.24 millijoules to be struck across the spark plug, in case of hydrogen, we need only 0.02 millijoules to create the initiate fire inside the engine. So it is a very small amount. But one difficulty is we should not have any hot spot inside the engine, like carbon deposit, which can create, which can initiate combustion inside the engine. Unfortunately, we don't have carbon in the fuel to form hot spot inside a hydrogen engine, but the oil that is passing the piston rings can form cakes after partial combustion and become a hot spot in a hydrogen engine. So we should try to avoid hot spot formation or cake formation due to the oil burning inside the engine. Okay. So what we can use simple glow plug also. We can use a hot wire to initiate combustion. But the regular spark arrangement of a gasoline engine can be easily introduced in hydrogen engine, because you don't need so many millijoules for creating the fire. So because the ignition energy is very less, the accidents can happen. There are places where hydrogen is stored, and if it leaks into the surroundings, even a small spark of very low energy can create a big fire. So what we have to do is we have to avoid unintentional mixing by using only hydrogen compatible materials and consider design and safety factors to prevent leaks. We should anticipate ignition mechanisms and control them so that we can ignite the hydrogen oxygen mixture at our will. Last is we have to adopt the best practices and implement safe practices with inspection, assembly, operation, maintenance, etc. So these three are to be taken care. And of course, we have said we can enable very high compression ratio. The theoretical auto efficiency says your thermodynamic efficiency increases as compression ratio increases. Higher the compression ratio or the specific heat ratio, higher is the indicated thermodynamic efficiency. So we can enable high value of gamma or ratio of specific heats by running the engine very lean. Okay, compression ratio is limited by resistance of the fuel to knock, and this fuel is knock resisting, so we don't have a problem. And a lean hydrogen mixture is less susceptible to knock than conventional gasoline and therefore can tolerate high compression ratios. So we are driving towards parameters. We can go for high compression ratio. We can go for a lean mixture for better efficiency as well as lower nitric oxide. If you see the thermodynamic efficiencies, you can beat diesel when you use hydrogen. That means you can get up to 5% better thermodynamic efficiency, or fuel consumption will be at least 10% better in case of hydrogen. And this 10% is based on the calorific value of hydrogen. If we consider the grams of fuel consumed, hydrogen consumption will be around 1/3 of diesel, basically because hydrogen has a lot of calorific value, that is calories per gram of hydrogen. So you if you get, in case of diesel, 190 grams per kilowatt hour, if you run hydrogen you will get around 80 grams per kilowatt hour. So now we have seen some of the chemistry. We will see the physics of combustion. We'll see the flame quench distance and backfire. Quenching distance is known for a long time as we have seen in Davy's lamp. This lamp was invented by Sir Davy for use in the mines. The flame inside the lamp will not propagate to the outside where there is a lot of combustible gases in the mines. The flame does not travel outside because the holes are so small that they so small or smaller than the quench distance, and the flame is quenched at the hole itself. We'll see one picture. If we have a small hole and if there is a flame propagating from left to right, it will be stopped at the hole because the hole has more surface area, and it loses heat vigorously. Okay, so the flame is stopped ahead of the hole. So this is the principle of Davy's lamp. The modern science says if you plot the quenching distance and spark ignition energy and on a log-log plot. So this is a logarithmic x-axis and logarithmic y-axis. You will find these two parameters, namely the ignition energy and the quenching distance, fall on a line. Isooctane, which is nothing but gasoline, is somewhere at the high end. That means it needs a lot of ignition energy, which we saw in the previous slides, and also the quenching distance is high. And hydrogen is at the lowest end. It has a very low ignition energy and a very low quenching distance. So ignition energy and quenching distance are basically arise from the same physical phenomenon. So we find this there is an excellent correlation between the two parameters, namely quenching distance and the ignition energy. We'll see a table here. You can see hydrogen has a quenching distance of 0.64 and gasoline 2.8. So we can handle gasoline somewhat better than hydrogen, especially near the valve seats. We'll see the example. Also, the ignition energy is shown here. Ignition energy is 2 for hydrogen, 2 10 raised to minus 5 joules, and for gasoline it is 24 10 raised to minus 5 joules. So quenching distance of hydrogen is very, very small. Therefore, hydrogen, in other words, hydrogen burns very close to the wall of the combustion chamber. And this can cause backfire. How does backfire take place? We have an engine here, and we cannot ensure perfect sealing between the valve and the valve seat in the cylinder head. And if the imperfect seating is larger than the quench distance, then the fire can propagate from the engine cylinder to the inlet air. So, and this can propagate up to our fuel admission point, and the entire thing can be a startling noise. It can frighten a person who is running the engine. Okay, so backfire can pass through minute gaps at the valve seats. Backfire in hydrogen-fueled SI engines is characterized using both experiments and CFD. So CFD helps a lot here to characterize this backfire. Of course, the fire can be sustained only if there is a temperature, sufficient temperature available. So hotspots minimum temperature for occurrence of a backfire is 950 K. It is around 670 degrees centigrade. So we should not have any hotspot, or if at all we have a hotspot, the temperature should be less than 670. So the spark plug or anywhere there is a carbon deposit, that should be having maintained at a temperature less than 670 by proper cooling. So hotspot's location does not influence backfire except for the timing of its origin. Backfire propagation is characterized by deflagration. Deflagration is not an explosive combustion. It is a gradual propagation of fire, but it can be irritating and sometimes frightening. So therefore, we have to maintain the spark plug and the exhaust valves or any other possible hotspots to temperatures less than 900 Kelvin, which is around 650 centigrade. So these have to be simulated by CFD to check the danger of backfire. Now we come to combustion only, the physics aspect of combustion. Higher diffusivity of hydrogen and lower density of hydrogen lower density of hydrogen must be considered. So we will see what diffusivity is. On the left side, you have, you have this yellow pigment dropped in both the glasses. On the left side, the yellow pigment diffuses fast, and the right it diffuses slow. So this liquid is the pigment has a very low diffusivity in this liquid, and on the left side the pigment has a higher diffusivity in the liquid. In case of gases, we can see an example. You can have a diaphragm and break the diaphragm. All of a sudden the gases on the left side diffuse to the right side. If you go to the molecular level, you can see the molecules are randomly moving inside the volume, and after the diaphragm is broken, they tend to diffuse towards the right side where the concentration is less. So higher diffusivity of hydrogen is pictorially shown on the right side, and it is a function of temperature. Hydrogen is having the highest diffusivity of all the gases, basically because its molecule is very small in size. And if you want to see the diffusivity of gasoline, it is somewhere here as shown by this red circle. On the left side, you can see the distribution of hydrogen soon after injection in the cylinder. It is uniformly getting diffused, whereas gasoline stays very close to the injector for a long time. So higher diffusivity of hydrogen is characteristic of its diffusivity property in air, and it creates a uniform mixture. Normally in gasoline engine we struggle to create a uniform mixture, but in case of hydrogen we get it very easily. And it enables complete combustion and hence improved efficiency. Also, because it is diffuses fast along with its enhanced flame speed, we can run the engine at very high speeds. Because it can run at high speeds, we can produce more power for a given volume of the cylinder. And because it diffuses fast, if at all it is let to the atmosphere, it will gradually go up in height, and the enabling reduction in danger. I mean, it is less dangerous to let out hydrogen in the open than letting out gasoline vapor. But the lower density is a big problem. We have seen the characteristic stoichiometric ratio is 29, but the volume occupied by hydrogen is 34% of the total cylinder volume for stoichiometric combustion. In case of gasoline engine, it is hardly 1.2% of the volume occupied in the cylinder. So lower density compared to gasoline makes a lot of volume occupied by the fuel, which otherwise could have been occupied by air. So we are unable to burn more fuel are as much as in gasoline, and hence a hydrogen engine, if run as a gasoline engine, would produce less power. Reduced power is generated when compared with gasoline because we can take in less fuel. It is like we say there is an elephant in the room. Okay. We need a very large fuel tank, and it occupies a lot of space in the vehicle. So we have seen both physical, chemical properties of combustion. We'll see how we can design a hydrogen engine. First, let us look at the heating value. The lower heating value is very good when we express in megajoules per kg. For hydrogen, it is far higher than a liquid fuel like gasoline or a gaseous fuel like natural gas. But its density is very low, as we have just seen. If we express the heating value per unit volume, you find liquid fuel wins hands down. So we need some special methods to handle hydrogen or handle this fuel inside the engine. Now we will see some of the chemical factors. Octane number is really good, 120 to 130. So we can go for a very high efficiency, as high as 17. At lambda equal to 1, the flame temperature is 2800 degrees centigrade. So the nitric oxide production is very, very high. So we cannot use flame lambda equal to 1. So let us see if we can run the engine at lambda equal to 2.2, which is the limit for lean combustion. So we can produce low nitric oxide. But when we look at the density, the fuel tank size is large and the engine power is low. We'll see a graph a bit later. And we can run the engine at high speed, which is advantageous. Quenching distance is very low, so we must be very careful while designing the engine. But it is possible by purely conventional and other methods to solve this problem. Diffusivity is very high. This is because the molecules of hydrogen are very small and it can diffuse very, very fast. So this can create some problems. We'll see how we can overcome it. A specific solution has to be found. So what are the techniques of fuel admission? We have port fuel injection, which is very common in case of gasoline engine. We can run it stoichiometrically correct ratio. We can use a three-way catalyst and run slightly at lambda equal to 0.95. But we have a problem. We produce high nitric oxide and use a catalyst to solve the problem. And also we have a poor efficiency at lambda equal to 1. Okay. But power is somewhat satisfactory. So some trials can be made, but these are not practical. We can run at lambda equal to 2.2 because hydrogen can burn very lean, we have seen. Either we can go for naturally aspirated or a turbocharged engine, we can see. When you go for naturally aspirated engine, we produce low power but high internal efficiency. But high internal efficiency coupled with low power will not improve the brake thermal efficiency. Actually, brake thermal efficiency would suffer a lot when we produce less power. That means the engine runs at very low load. Of course, we can avoid a NOx catalyst because we are producing low nitric oxide. But if we can turbocharge and run at lambda equal to 2.2, we can avoid the NOx catalyst, have satisfactory power produced, higher efficiency, and low nitric oxide. But these are for port fuel injection, okay? But still, the fuel occupies a lot of volume, even if we turbocharge, that means 34% of the volume. So we are not able to produce as much power as it is capable of if it were admitted, if the fuel were admitted like in a gasoline engine. So we will see the next possibility. We admit fuel directly in the engine at lambda equal to 2.2, that is in the main chamber, and provide a small pre-chamber. We will see an example. We can produce satisfactory power at high efficiency, low nitric oxide, and suitable for heavy duty application. But is it all? We can go for active pre-chamber where both the spark plug and the fuel admission are taking place inside the chamber at lambda equal to 2.2. We can generate satisfactory power, higher efficiency, low nitric oxide, and we can even have a naturally aspirated engine. But we can go for a turbocharging to further increase the power. So we can see only we have three options as shown here, and in two cases we have to turbocharge. Okay, in two cases we can turbocharge, but in pre-chamber passive we can either turbocharge or naturally allow the engine to be naturally aspirated. Ignition energy is very low, therefore igniting hydrogen is easy. Gasoline injection systems can be used, ignition systems can be used. However, at very lean air-fuel ratios, if at all you want to run at that, the flame speed reduces considerably and the use of dual spark plug system is sometimes preferred. But this is for an engine where we have spark plug and fuel admission are in separate chambers. A waste spark system, which is very common in gasoline engines, should not be used for hydrogen engines because any remaining hydrogen can be easily ignited, and this can cause this wasted spark can be a source of pre-ignition. In case of gasoline engines, we very often resort to waste spark systems. That means we spark both at the end of compression or during the compression and during the exhaust stroke. This makes our circuit design a bit simpler, and it is less expensive than non-waste spark systems. But we have to spend a little money extra for hydrogen engine to avoid wasted spark system. And the spark plug must be cold rated. We cannot use a hot rated spark plug. A cold rated plug transfers heat from the plug to the plug tip to the coolant in the cylinder quicker than a hot rated spark plug. So this avoids any chance of spark plug tip igniting the charge when there is no spark. This is basically because we have a very low ignition energy requirement for a hydrogen fuel mixture. Incidentally, we use hot rated spark plugs deliberately in case of gasoline engines so that carbon deposits are not accumulated near the spark plug. Once carbon deposit accumulates near the spark plug, the spark either weakens or the spark is short circuited. In case of hydrogen, there is no carbon, so we don't need hot rated spark plugs. And we should not use platinum tip spark plugs at all, because platinum is a catalyst and it can cause uncontrolled hydrogen combustion. So we have to differentiate between gasoline and hydrogen engine only in the spark plug layout. Crankcase ventilation is a very important subject. Unburned fuels seeps past the piston rings and enters the crankcase. Since hydrogen has a very low energy ignition limit or low ignition energy than gasoline, any unburned hydrogen entering the crankcase has a greater chance of getting ignited. Hydrogen should be prevented from accumulating by proper ventilation of the crankcase. Ignition within the crankcase either can be a startling noise or result in an engine fire. Engine can catch fire at the breather. When hydrogen ignites within the crankcase, there is a sudden rise in pressure, and this is what causes the noise or the engine fire. Therefore, what we need is a pressure relief valve to relieve this pressure instantaneously, and this is usually installed on the rocker cover. Many times we introduce pressure relief valve even for our CNG engines. Now, not only hydrogen, also the burnt gases can seep by the piston rings into the crankcase. Since the exhaust is water vapor, water condenses in the crankcase when poor ventilation is or when proper ventilation is not provided. If there is no proper ventilation, the water will condense, and mixing of water into crankcase oil reduces lubrication ability, and this will result in higher engine wear. There are some oils which don't retain water and water can be separated. So when we specify oil for a hydrogen engine, we should specify special oil which will which will settle water at the bottom of the sump, and that can be drained. This is apart from our effort to ventilate the crankcase properly. So we see hydrogen combustion engine. We make a comparison here. On the left, we have a gasoline engine where we have admission of fuel in the port, and we can produce, say, power 100. If we allow hydrogen similar to gasoline in the port, we can produce only a power which is 85% of a corresponding gasoline engine. So the other one is, so we produce lower power if naturally aspirated, and you might need very high boost ratio for turbocharging. If you go for turbocharging to increase the content of air and hydrogen inside the engine. But the boost ratio is very high and you need very special turbocharging. You can have insulated manifold and inject liquid hydrogen in the manifold. Then we will get around 115, slightly more power, 15% more power than a gasoline, which is good, but you have to have liquid hydrogen stored in the vehicle. Alternately, we can have a high pressure gaseous hydrogen injected in the pre-chamber, and we can produce 120% of gasoline power, and this is an excellent method because you don't have to handle liquid hydrogen, which is a very complicated, which needs complicated engineering. And we can work with a reasonable boost of 2.5, even with a turbocharged engine. So we will see how we select the engine combustion. You can have stoichiometric combustion, you have high nitric oxide, so better we avoid stoichiometric combustion. We can have lean lambda equal to 2.2 combustion. We have low nitric oxide, so one big headache is solved. Whether we go for naturally aspirated or turbocharged, we have to make a decision. We will produce less power with naturally aspirated option, so we would like to rule it out. If you go for turbocharging the engine, you can produce relatively higher nitric oxide, higher boost. So it is not very nice. If you go for turbocharging and intercooling, we can produce very low nitric oxide, and we prefer that design. We have various options of admission fuel. One is port fuel injection. It demands very high boost if at all we turbocharge, because we want to turbocharge the engine. And boost is 3.5, which is very high. We would like to avoid it. We can go for direct injection of gas in the cylinder. Boost is 2.5, okay. We have a choice whether we have a pre-chamber or a no pre-chamber. If there is no pre-chamber, the hydrogen diffuses fast and ignition limit problems occur. Also, backfire can happen because this fuel air mixture can leak past the small gaps, and special material for hydrogen embrittlement everywhere inside the engine. So we would like to avoid it. Then you have an option to go for a pre-chamber. In the only the pre-chamber will be of special material. We can go for passive or active pre-chamber. When you go for passive pre-chamber, you have backfire and special material for hydrogen embrittlement, because the fuel is injected in the main chamber. We will see the picture. So we'd like to avoid that. You go for active pre-chamber. There is no backfire, special material only for the pre-chamber, and you can make a choice. So this is the tree or choice tree, and how we arrive at this system. So this picture shows arrangement of port fuel injection, and it is a naturally aspirated engine. So it generates very low power. It has beset with a lot of problems like backfire, low power, ignition control problem, etc., etc. Okay. So this is a port fuel injection. Many times in the early development, many laboratories tried this, but we would like to avoid this. And we saw the emissions are dropping substantially as lambda is, or phi is decreasing or lambda is increasing. So we would like to operate at very lean limit of the flame. And on the right side, you have a comparison with gasoline. In case of gasoline, you have additional emissions like CO and HC. And here you have only nitric oxide emission. Incidentally, we cannot use a three-way catalyst very well at lambda equal to 1 for hydrogen. We have to run it slightly rich so that hydrogen is available in the three-way catalyst. But anyhow, in the previous slide we saw we would like to avoid stoichiometric combustion, so there is no question of three-way catalyst at all. Okay, so we have to treat only NOx emission, which can be done with lambda equal to 2.2. So NOx control in hydrogen engine is by running at very low, very high lambda or very high air fuel ratio. We run at very high speed and we control the ignition timing. Also, we can introduce small amount of EGR for reducing the flame temperature, even at lambda equal to 2.2. So this is a technique only for academic study, where you can use a catalyst at lambda equal to 0.9 and reduce all nitric oxide to nitrogen and water. But at what expense? We have very poor combustion efficiency, as well as we produce less power. So this is a thing which we would like to avoid. So we compare two combustion, one lean mixture which is at lambda equal to 2.2 and one at lambda equal to 1. This is the rate at which heat is released inside the engine. You can see a lot of heat is released in a pulse in the initial portion, and it produces very high nitric oxide. Here we release heat very gradually at low temperatures, and correspondingly we have less nitric oxide. If you see the right side, you will see the brake thermal efficiency improves as you make the mixture lean and lean. The brake thermal efficiency improves from 27% to 34%, which is corresponding to 30% improvement in the brake thermal efficiency. Sorry, brake specific fuel consumption. 30% improvement in the brake specific fuel consumption. Why this improvement is taking place? It is because of the reduction in pumping losses. We handle less and less hydrogen and air to be pumped into the chamber at high depressions. Okay. So this is a heat release from the residual gas, follows the main combustion of hydrogen at lambda equal to 1 that we have seen. Thermal efficiency increases up to 34% with pumping loss reduction at lambda equal to 2.2. Combustion loss is not very high, 0.32%. Okay, these are some of the numbers. We again want to reiterate the reduction in NOx at lean conditions. You can see that NOx is 4,390 ppm at lambda equal to 1, or when it is stoichiometric combustion. When we run lean, we can produce as low as 14 ppm. So the choice is lean combustion, and we can run stably at lambda equal to 2.2. Lastly, we come to turbocharging. For clean combustion of hydrogen, turbochargers have to provide around twice as much as air mass as they do in gasoline engines. That is because we are running at lambda equal to 2.2. However, lower exhaust temperatures result in a lack of energy for the production of further propulsion for running the turbocharger at the turbine. This discrepancy cannot be resolved with conventional turbochargers. So special feature of the turbocharger is the coaxial arrangement of two compressor stages, which are driven by the turbine or the supporting electric motor using a common shaft. The process air flows through the first compressor and is cooled in the intercooler, then again compressed in the second stage. So we'll see some pictures. These are some V engines. We have here a single stage turbocharger, but here we have a two-stage compressor. The output of this compressor is cooled at the intercooler, then again goes to another compressor, and after increasing the pressure, it goes to another intercooler for better cooling, and the temperature maintains around 20 degrees above room temperature and fed to the inlet manifold. So two-stage compressors with intercoolers are very common. If we don't want that, if you can have an electric motor-driven compressor. You can manage these valves in such a way that the output of one compressor goes to another compressor, and then we increase the pressure and goes to the intercooler. Or we can have an arrangement as shown on the right, the boost second stage compressor, which is run by an electric motor, can be either bypassed or allowed to run to increase the pressure. So these are various possibilities. So the control becomes very complicated. We'll see some simpler systems also. So this turbocharger has got an electric motor which will enable the compressor to run when the turbine is not getting sufficient energy. In fact, the turbine housing is well insulated to save whatever the thermal energy it can save in the turbocharger. So this utilizes high-speed electric motor positioned on the turbo shaft to spool the compressor more rapidly and also eliminate lag. It dramatically improves the transient engine performance and low-end engine torque. It provides more power and faster response while further enabling the engine efficiency. This is another way of having a two-stage turbocharger. You can see there are two compressor stages, one on the left and another on the two turbines, one on the right and another on the left. Okay, so the engine out exhaust gases flow into this turbine, and the outlet of this turbine is fed to an axial turbine here, and the gases flow out to the silencer by this path. You have two compressors. This is the first stage compressor, and this is the and it is cooled after first stage compression. Then it goes to the second stage compressor, and totally we can have compression 4 to 5 times that of the atmospheric pressure. And because of intercooling, the temperature will be around 20 degrees higher than the room temperature. By splitting compression between two turbos, both the compressors operate at peak efficiency. Also, the lower pressure ratios for each stage mean lower rotating speeds, which results in improved reliability for the bearing systems, compressor wheels, as well as the turbine wheels. Of course, we can introduce VGT. You can have narrow vane opening or wide vane opening and manage very high compression ratio in the turbocharger, but not better than 3 for small engines. We have to have special materials to withstand hydrogen embrittlement. The valves and pre-chamber must be made of stainless steel 316L, and we should have hard face for the valves so that there is no leakage of hydrogen air mixture in the valve seat gaps due to wear and tear. A lot of material choice for hydrogen engine is available in this reference. I request the audience to search in this reference for the suitable materials. So now we are narrowing down to heavy duty lean burn, and there are direct injection engines with pre-chamber system. We will see gasoline and then we will see hydrogen. Okay. So the IC engines are continuously improved with compression ratio increase and use of Miller cycle. These IC engines are running using gasoline. Okay, and they have passive pre-chamber with a spark plug in the pre-chamber. Okay, and the fuel is injected in the main chamber. There is no risk of backfire in case of petrol engines. Then you have cool DGR with both passive pre-chamber spark plug and active pre-chamber spark plug. In active pre-chamber spark plug, we inject fuel in the pre-chamber. So this is just coming up. Okay. So how is it done? The pre-chamber is looking like this with cooling passages. Okay. And we'll see a movie, of course. And the spark plug is inserted in the pre-chamber. The fuel is injected in the main chamber. Okay. And this fuel air is mixed. Fuel and air are mixed well during the compression stroke, and the fuel air mixture is pumped into the pre-chamber through these small holes here. There is a small hole here, 4 or 5 holes. So it is pushed into the pre-chamber. At the right timing, spark ignites the fuel air mixture in the pre-chamber. And once it ignites, there is a sudden increase in pressure, and the fuel air mixture that is burnt rushes through these holes in the form of jets. So essentially what we are having is a very extended spark plug in the form of jets, and that can fire very lean mixtures effectively. We'll see a picture. So this is how the pre-chamber looks like, and these are the holes, and this is the fuel injection fuel injector. And when the fuel air is mixed and the compression during the compression stroke, the piston is moving upwards, the fuel air mixture is pushed into this pre-chamber, and the spark ignites the fuel, and when it is ignited, the pressure rises and you produce intense jets. And the entire fuel air mixture in the main chamber catches fire and burns, and it produces power. So there is, if you have a regular engine with a spark plug in the main chamber, the rate of heat release is as shown in the blue, as shown by the blue curve. If you have the pre-chamber arrangement and a spark plug inside the pre-chamber, we get a heat release which is really fast, and this causes this increases our efficiency, and more surface area and faster heat release, and hence better fuel economy. Up to 4% improvement in fuel economy is possible, as we see on the right side, a graph of fuel consumption, specific fuel consumption. On the other hand, we have active pre-chamber spark plug system. We have a GDI in the pre-chamber. The fuel is injected in the pre-chamber, and there is a spark plug as we have seen in the passive pre-chamber, and we have a very, very rich mixture inside the pre-chamber, but we know hydrogen can burn either very rich or very lean without much of the problem. The average air-fuel ratio is around 2.2, but when the spark is occurring inside the pre-chamber, in the pre-chamber we have a very rich mixture. So usually it will be very difficult to start combustion because of the flammability limit problems if the fuel was anything other than hydrogen. But here, because we have hydrogen, we are able to manage good combustion. This has to be tried a bit on computer for the residual fraction around the spark plug, because it is possible that during the small period when the fuel is, some amount of fuel is burning in the pre-chamber, we end up producing very high nitric oxide. So to avoid that, we use this idea of having some of the exhaust gases very close to the spark plug, and the fuel, not sufficient fuel is made available near the spark plug, and this reduces nitric oxide. As we have seen, the active pre-chamber can run at very high air-fuel ratio, or lambda equal to 2.2, and this system can offer very good fuel consumption or very low fuel consumption. And this is lambda equal to 2.2, and you have a very low fuel consumption compared to a simple system of having a spark plug in the main chamber. Also, we can extend the combustion safely up to 2.2 without having any problem of flammability limits at high speed engine running, and this reduces nitric oxide 50 times compared to the stoichiometric combustion. And this also improves the fuel consumption. Up to 9.7% improvement in fuel economy is possible. And of course, a lot of CFD is necessary, computational fluid dynamics, to locate the spark plug and locate the fuel admission valve properly, so that we have some advantage regarding nitric oxide and fuel consumption.
Never before has it been so important to cut fuel consumption and pollutant emissions of vehicle powertrains. To achieve the future fleet target of less than 75 grams of CO2 per kilometer, the efficiency of combustion engines must therefore be significantly enhanced. Pre-chamber ignition is a technology that helps to make combustion more efficient. It has been used for many decades in stationary large-bore gas engines. The pre-chamber is currently also used in Formula One racing for high-performance levels in highly dynamic operation. How can these two worlds be brought together? IAV has selected a new approach to the pre-chamber and developed solutions that make future use in passenger cars highly promising.
Usually, when we're thinking about pre-chamber spark plug, it's just a spark plug with a cap on it. We wanted to go a different way. We wanted to integrate the pre-chamber spark plug into the entire engine. So it means, on the one hand, integration into the combustion process, and on the other hand, the integration of the pre-chamber into the cylinder head itself.
The principle is simple. After the fuel mixture has been ignited in the pre-chamber, flare jets pass into the main combustion chamber. Here, they act as multiple space-filling ignition points for constantly stable, rapid burning of the mixture, providing major advantages in terms of both knock and consumption in stoichiometric operation.
when we think about putting a pre-chamber spark plug into a serious car, we have to cope with several problems. On the one hand, we have very high loads and very low loads. And on the other hand, we have also very high and very low temperatures. And in addition to that, we also have to make sure to enable catalyst heating. And we at IAV, we found some solutions to exactly these problems.
We see pre-chamber ignition as an evolutionary technology. On the one hand, we are working on a passive solution where the mixture only gets to the pre-chamber via the main combustion chamber. This is a low-cost variant that is easy to implement and achieves 2 to 3% fuel reduction in our tests. On the other hand, we are also developing an active version with an additional special air-fuel low-pressure injection system, achieving 7 to 8% fuel savings. It enriches the mixture in the pre-chamber to such an extent that optimum ignition conditions prevail in the pre-chamber, even with extensive charge dilution. In contrast to other active pre-chamber systems, tests with IAV's active solution revealed particularly low HC and particulate matter emission levels.
Further tests with the pre-chamber, in combination with other technologies like the Miller cycle or high external EGR rates, have confirmed the high potential that the pre-chamber has. Based on that, we are convinced that it is an evolutionary technology which can be used in future powertrain concepts.
Pre-chamber ignition is part of the intelligent powertrain that we are developing with and for our customers. Our pre-chamber ignition solution is an investment in the future.
So we have active pre-chamber systems available from companies like Mahle that you can introduce in our cylinder heads, for example, and then develop a good hydrogen engine. And such such engines are developed by Liebherr in Germany and JCB in the UK, and they are really heavy duty engines which run at 70 to 75% full load constantly. Now we will see this system for available for development of hydrogen engine. You can get this special pre-chamber with injector and spark plug from well-known fuel injection companies, and you can introduce that into the cylinder head design, okay, and create an active pre-chamber system. So here we see a movie. So we, as a summary, we can have an active pre-chamber system with ultra lean operation up to lambda 2.2 or 2, with 10% improvement in fuel efficiency and 95% lower nitric oxide as at the engine out, and of course we avoided knock in the engine. With this, I would like to conclude my presentation by showing how we selected. We will just go through the route again. We have hydrogen. We chose lean combustion for low nitric oxide, and we selected turbo intercooled engine, and we went for direct injection with say boost 2.5 for enhanced power. Then we went for pre-chamber option, and in pre-chamber option we preferred active to passive option. There is no backfire. We need one special material only for the pre-chamber, and we have a nice hydrogen engine where we can use we can use the same material as we have used for our regular engines, except for the pre-chamber and probably for the valve. Thank you very much for your attention. There are some references given. Those who are interested can read this. Thank you again.
Thank you so much. Thank you so much, Dr. Lakshminarayan sir. So much of in-depth technical knowledge sharing, starting from engineering, chemistry, and physics, based on data, facts, and conclusion on design of heavy-duty hydrogen engine. Thank you so much, sir. And I see in the chat box a lot of the comments, appreciation comments are coming up, and also Dr. S. Devarajan sir has also joined with us in the session. He's senior vice president BCIC and senior vice president TVS Motor. Thank you, sir, for joining.
Very, very interesting, Dr. Lakshminarayan. Outstanding. I think I learned a lot of things. I joined a little bit late, but very, very interesting. I think we should have a much more detailed discussion with you. One of few questions I have is, will it cause anything on the emission atmosphere, which causes headache and other dizziness if it leaks to the atmosphere?
No.
That's one question.
No, if hydrogen leaks, it goes up in atmosphere because it's very, very light.
Yeah.
So it is said that there is no danger if it leaks. But if BMW have developed some hydrogen based vehicles, fuel cell vehicles, etc. But they advise not to have the vehicles inside a garage. They want us to leave the vehicle to open till they prove the safety of the vehicle in closed spaces. So a hydrogen vehicle must be left in the open, because even if hydrogen collects inside it goes up, if it cannot escape into the atmosphere, it can collect at the top very near to the ceiling, and a small spark, maybe two iron rods clashing against each other, can produce a spark and create a big fire. So only thing is, we must leave the hydrogen vehicles in the open till the experts advise some methods.
One more question I'll ask. Only thing is, the size is going to be a big problem in terms of the hydrogen, because of the density and usage of the hydrogen cylinder holding it. Is there any work being done on the cost analysis portion of it?
Yeah, the cost is very, very high, as you said. The gas has to be stored at 700 bar, but we are used to having CNG at 240 bar. So it is an increase in pressure, and special cylinders have to be used. Another option is to use liquid hydrogen, and you can inject liquid hydrogen straight into the engine. The problem with liquid hydrogen is you need to maintain it cool. So every 17 hours, you have to release some of the cold hydrogen liquid, allow it to evaporate and cool the main tank. And it is said if you don't run hydrogen engine continuously, you need to waste this much fuel, and it can go up to 20% for those who are transporting liquid hydrogen from one place to another place, up to 20%. So this is the estimate given. Yeah. So in a car, you will have to cool it once in 17 hours by releasing around 2% of fuel if the car is idle. But you have always the choice of storing it at high pressure, 700 bar. But you don't need 700 bar for injection. You need hardly 250 bar maximum. So you have to drop the pressure somewhat and allow it to the injector before it is admitted to the cylinder.
But very interesting, sir. I think we should now see how to use it for the lower capacity. Anyway, it's a big research work, but useful for the emission and for the future emission.
Yes.
It's going to be very, very important because there is no NOx or Red Sea. It's only, very, very important point.
Suitable for heavy duty engines, I think. Very heavy duty, like earth movers, cranes, or trucks. Not even buses, I think, but trucks. You can use it very effectively.
Yeah. Thank you, sir. Over to Ravindran. Thank you, sir, very much for the excellent.
Yes,
Thank you.
Thank you, sir. Sir, due to limit of time, I'll just take two questions. One is from Saurabh Misra. He says, thank you, sir, for the presentation. Please tell about engine power and suitable application for this engine. Does these engines are suitable for mining and construction machinery?
Yes, it is suitable for mining and construction. And in fact, the pioneers of such engines are JCB and Liebherr, for example, which are in the off-road doing earth moving operation. And for, of course, we can use it for passenger cars. You have to have a big cylinder in your boot or somewhere to hold this hydrogen, and special hydrogen cylinders. Otherwise, the cylinders will become very heavy. So you need carbon fiber reinforced plastic tanks which can stand 700 bar. Of course, they are available, and as I said, BMW is having hydrogen car. Toyota is having a hydrogen car. Okay.
In fact, one of the vehicle Toyota I just drove last month.
Yeah.
I experienced that.
Yeah.
So, Mr. K. Ganamani is saying, very good presentation. Thank you, sir. Any country, if success in this hydrogen engines, share the successful completion, sir.
Yeah. I heard this JCB has said is put this engine in production, and they have built the 1000th engine, which is not a very big number, but I think in another 20 years we will have a lot of hydrogen available. You will have also hydrogen everywhere. I mean distributed, not only hydrogen produced and distributed. By that time, the engine and vehicle manufacturers must be ready with this engine which runs on this fuel. So if normally about 7 years is the time for developing any engine or vehicle. So if they start now, they will be ready by 2030, by which time I think there will be hydrogen available almost everywhere. 30 or 35. Yeah.
Thank you, sir. Sir, there's last question. Mr. VM Madhavan says, great insight has been given, sir. Thank you. And then he has got, can we allow hydrogen in existing petrol engine for testing? What even if you do this?
Yeah, you have to design a new cylinder head, and wherever you have a spark plug, you remove that. You have to design a new cylinder head and accept this kind of sub-assembly, which has both a pre-chamber fuel injector as well as the spark plug. Okay. Of course, we know what we expect, what are the special characteristics of the spark plug, etc. So this can be adapted into the existing cylinder head layout, but it will be a new cylinder head by design. Layout will be similar, but in a 4-valve engine it will be fairly easy. In a 2-valve engine, you have to find a place to accommodate this pre-chamber. Okay.
Thank you so much, sir.
Thank you.
Thank you so much.
Thank you, sir. Thank you.
Sir, thank you for your answer. And thanks to all the participants for patient listening and asking nice question. And thanks for your kind word. Thank you so much, Dr. Lakshminarayan, sir, for
you.
nice, wonderful session. And now over to Rupa ma'am. Rupa ma'am, please.
Thank you, sir. Thank you very much, sir, for your exhaustive presentation. We look forward to have many more sessions in the future on the subject also, sir.
Thank
We
you,
would be
madam.
very happy to host you at our office, sir. Please do visit us whenever you are there in Bangalore.
Yeah, thank you. Thank you.
Thank you very much, sir.
Thank you.
Thank you, Alana.
Thank you. Bye.
Thank you. Thank you very much. Thank you.
Thank
all.
you.
Thank you, sir. Thank you, sir.